Hello everyone, welcome to Caltex Academy. Today we are looking at classical mechanics. We have a question here that talks about a particle of mass 2m rests on a rough plane inclined to the horizontal at tan inverse of 3 mu, where mu is the coefficient of friction between the plane and the particle. The particle is acted upon by a force P acting along the line of the greatest slope. If the particle is on the point of sliding up the plane, so that the maximum force required to maintain the particle in equilibrium is 8 mu mg over root of 1 plus 9 mu square. So let's sketch a diagram such that we shall be able to figure out exactly the force that would be required to maintain this body in equilibrium. Resolving vertically to the plane. Along the plane, up is positive, so we'll have R is equivalent to the resolution of this force to mg in the vertical direction to the plane. So here we'll have R and it's acting in that direction, meanwhile this one is acting in a different direction, so minus 2 mg cos of theta must give us 0. So when you take to the other side, we will have our R equals to 2 mg cos theta, and we can call this one here equation 1. Now let's do the same. We resolve in the horizontal direction, taking in that direction to be positive. From our diagram, we can see that P has been balanced by this force and this weight. So we will have P minus 2 mg sine of theta, and we have been told that the coefficient of friction is acting, so meaning we have some force here F acting in this direction, so the sum of these forces must be equal to the upward force P. So if that is that, we sum this one equals to 0. So we can take it to the other side and we shall be having here P equals to 2 mg sine of theta plus F, and F is equals to mu R. So we can write there mu R, where mu is the coefficient of friction and R is the normal reaction. So we can call this one equation number 2. Having done that, we will combine these equations together because our R is in equation 1, so we can substitute equation 1 in equation 2. Substitute equation 1 in 2. So P will be equivalent to 2 mg sine theta plus mu, and this one is 2 mg. So we'll first write 2 mu mg cosine of theta. Now we look at what is common and we factor it out. So the common factors here are 2 mg into sine theta plus mu cos theta. So when you look at our question here, we have been given theta equals to tan inverse of 3 mu, and from this triangle, when we have theta is equals to tan inverse of 3 mu, we can have here tan theta equals to 3 mu, and this one stands on over 1. So from TOR, which is tan is given by opposite over adjacent, our opposite is 3 mu, then adjacent is 1. So when you use Pythagoras theorem, the hypotenuse is going to be this, and then there we can take sine and cosine of this angle theta. So sine of that angle theta is given by opposite over hypotenuse from here also. So our opposite here is 3 mu, and then hypotenuse is this, and we have 1 plus 9 mu square. Then cos theta is given by adjacent over hypotenuse. So our hypotenuse here is the same like this one, so we will have our adjacent to be 1 all over 1 plus 9 mu square. So we can hurry this one and substitute to our equation, our combined equation here. So we shall have P equals to 2 mg into bracket our sine theta is given by our 3 mu over 1 plus 9 mu square, and then plus mu times 1 is going to be mu, and we have it also over 1 plus 9 mu square. So we close this bracket and we have common denominator. We can just simplify it by combining the denominator together, where we have mg equals to, in bracket, just we add these two together, we have here 4 mu, and a common denominator 1 plus 9 mu square. And then after that we can open up this bracket by multiplying with this coefficient 2 mu g, meaning our P is equivalent to 8 mu mg all over under root of 1 plus 9 mu square as required. So that is the force which is responsible for balancing this body from sliding down, and that is P, which is equivalent to this. Please support this channel by subscribing, like this video and share with friends. Thank you and see you next time.